Let's just wait for a few more minutes until others will join and then we can get started. Can you please confirm if I'm audible in the chat? So final exam pattern that is typically not set by us. So we usually take the live sessions. You can maybe ask it in the forum discussion forum, and I think you might be also receiving some like last year similar study material or exam sample exam questions or something like that. So maybe you can see based on that. But yeah, I'm not really sure, but I don't think there will be any coding examples. But again, please confirm once with uh, in the discussion forum in the SWIM portal. Uh, let's get started. So, good evening, everyone, and welcome to week 11 of this live session for the course Deep Learning for Computer Vision, conducted by Professor Vineet and Balasubramanian. Uh, so this is almost, I think, the second last week in this entire course, and we've covered a lot of different topics. And we also saw about different, we started off with very simplistic algorithms of saw what is a neural network. We discussed about ways to optimize a neural network, and then we moved into the more fundamental neural networks like CNNs for images. Then we saw several different types of CNNs, and we also then discussed how these CNNs can be used for not just image classification tasks, but even for complicated tasks like um, uh, object detection, semantic segmentation, and then we also discussed about complicated tasks like image captioning and visual question answering, which for those particular tasks we use something called as sequence to sequence models like RNNs, LSTMs, all those things. And then finally we moved into attention models and the most popular attention based neural network, which is transformers, which is very widely used in today's world, like all your chat gpt or LLMs like Gemini, any LLM which you think about, all of them are built on top of transformers. Of course, there are different variants to transformers, but yeah, the fundamental mechanism is still self attention and multi-head attention, multi-head self attention, basically. And then we moved into last week we talked about the generative algorithms, which are different from discriminative algorithms. I hope that distinction is very clear. How discriminative algorithms try to just discriminate or like just map the input to the output. That input X, how is it? Which particular input X should be mapped to which particular output Y? That is the only concern for the discriminative models. Whereas in generative models, the idea is to learn the underlying distribution of the input data. So it's not just mapping input to output like a black box, but is also to understand what is the fundamental and input distribution that is being given to the neural network. So that is the generative algorithms. And of course, once you learn the underlying distribution, you can also solve a lot of discriminative tasks too. But the goal is to learn the underlying distribution. And we saw different ways to do that. So we started off with the most simplistic thing, that is the VAE algorithm. Let me just quickly recap that. I'm recapping the generative algorithms because today we will touch upon one of the most popular recent generative algorithms called diffusion models. And so it's important for you to understand the background of the different algorithms that were there previously, so that it will be better for you to understand where diffusion model comes from. So the most simplistic one diffusion algorithm which we saw was VAE algorithm, which stands for variational autoencoders. So these, as the name suggests, these were built on top of autoencoders, which are very popular in learning the latent representation of the given input. Now, what does it even mean, learning the latent representation of the given input? So it typically means that, let's say if I have a neural network like this, and I have an input X, then the network typically has like some hidden layers. There could be multiple. I'm just drawing three for simplicity, and then there is an output network. And the output is trying to predict, yeah, the output is trying to predict X itself. Let's call it X hat. So the goal of this autoencoder, again, it's a think of it like a simple multi-layer perceptron. The goal of these autoencoders is X hat should be as close as possible to X. Now, what are we doing when we are creating such a network is we are learning this hidden representation of the input X. So if I take this vector, which we typically call like a latent vector, latent is nothing but hidden. That's the actual meaning of latent. So we are trying to learn these latent vectors so that we can now represent the input data using just these latent vectors. And why are we so sure that this latent vectors are a representation for this input X? Because if you look at it with the help of, so think of this particular chunk, uh, think of this particular chunk to be like an encoder, and think of the right side chunk to be like a decoder. So we are basically saying that I take X, I send it to the encoder. The encoder is projecting into some latent vector. Now, just using this latent vector, the decoder can generate X hat, which is very similar to the input X. So technically, this latent vector should be a representation of that X, right? So that is what logic dictates. Because from this latent vector, I'm getting the same output, which I'm getting an output which is similar to the input. So it means that this latent vector is a representative of that input X. So this was the fundamental idea of creating these autoencoders. Now, what does the variational autoencoder do? The the trick is in this variational part. So what it suggests is latent vectors. The autoencoder, what it does, latent vectors is a fixed vector. So your input X maps to a fixed latent vector, and that fixed latent vector will generate the output X hat, which is close to input X. But this is not very helpful if you think about it, because what are generative algorithms? Generative algorithms need to learn the underlying distribution. But with this latent vector, I'm only learning the representation of the samples which I have, of the training samples. So l- let me make it more clear. Let's say I have a distribution P of X. Okay. And of course, we don't know the entire true distribution. Now, how do we typically solve any neural network, any deep learning problem? We sample from this distribution a data set. Let's call it dx. Now, this data set is fixed. Like typically, um, the number of samples in a data set is like n. Okay, so we have a fixed set of samples, which we assume to be sampled from this distribution p of x. Now, based on this fixed sample, we want to learn what is the underlying distribution. Now, if you use autoencoders directly, this particular learning, this reverse learning of the samples to the distribution will not happen, because this latent vector, this is a fixed vector. And this fixed vector will only learn the representations of the given n samples. It will not learn all the other samples which might be possible in that particular distribution P. So to overcome this, in variational autoencoders, they say instead of learning a fixed particular latent vector, learn a distribution. And what is the distribution which we saw? Learn a Gaussian distribution. So we all know that the Gaussian distribution needs two parameters to completely define that Gaussian distribution. What are the two parameters? This is how we typically represent. You need mu and sigma. So mu stands for the mean. I think this everyone knows, but let me be very clear. Sigma stands for standard deviation. So if you just know these two parameters, you'll know what the Gaussian distribution is. So latent vector basically does variation autoencoders basically does this. It will try to learn what is the mu and sigma, and if you know mu and sigma, you'll know this Gaussian distribution. And if you know the Gaussian distribution, then you can generate from then you're basically modeling this p of x as a Gaussian distribution. So now you can sample data points from this particular distribution which were not there in the training data which you had. So this is how generative algorithms work. Now, one obvious problem which we see in VAs is you can't really learn a smooth uh, latent vector. Like the latent vectors which you learn, even the distribution, there will be a lot of gaps in between the way in which, because of the way we formulate this entire problem. So that's why we say VAs doesn't learn a smooth latent representation. It kinds of learn a more way up and down discrete type of a latent representation. Now to overcome these problems, what people have come up is the second algorithm is GANs, which again, these are all concepts which we saw. I'm just refreshing it to move to diffusions. This stands for generative adversarial, sorry, generative adversarial networks. The idea behind GANs is again very simple. Let me just erase this first. We still try to learn this mapping. The distribution mapping is not changed. We still want to learn that itself. But how do we do it in GANs? In GANs we use two networks to do this learning of going from samples to distribution. One we call the generative network. One we have a discriminative network. Generative network will take any random noise point and it generate some output which will look like x hat. Let's say. Then we also have a real data x. Now the discriminator's job is it takes these x and x hat and tries to identify whether it's a real or a fake input. Now this generative is model network which is there, right? That is inherently learning this p of x. Okay. Why do I say that is learning? Because if I in an ideal situation, we want the generator to fool completely the discriminator. And how can a generator fool a discriminator? When if it can take any random Gaussian, any noise, not just Gaussian, if it can take any noise and it can completely generate an output x hat, which will look exactly like it is coming like an original image x, means it is being sampled from this p of x. Now that is only possible if G knows what p of x is. So that is the idea. So G is basically learning the distribution p of x, and that is why it is able to generate an output which is very close to the real image, and that is why discriminator is not able to differentiate between these two images. So just like how in VAs we learned the p of x using the latent vector, in GANs we learn using the generator network. So GANs again obviously have, we discussed the issues with GANs, is that the training might be a bit tricky. It might not be very easy to train. It might need you might need a lot of hyperparameter tuning. You might need a lot of other optimization techniques to be done. And also GANs do generate very good images, and it also can generate smooth continuous space. So VAs were discrete, GANs do a smooth continuous space. Now, the third algorithm, which is the main focus of today's session, is diffusions. Let me go there. Now, diffusion again comes with a very different formulation. It again is a generative algorithm. It is also trying to learn the P of X. That is, the objective still remains this backwards pipeline. This is what we're trying to learn, P of X. But just that, how will diffusion do? So diffusion has two processes. So we have number one called the forward process. Let me write it this way. We have a forward process, and then we have a reverse process. Be very careful that this is not the forward pass and the backward pass of neural networks. This is not that. This is diffusion's forward process, this is diffusion's reverse process. This is nothing to do with the neural network forward pass, backward pass. Okay, that needs to be very clear, because it's very easy to get confused coming from the deep since we are so used to talking about forward propagation, backward propagation in neural networks. It is definitely confusing. It was confusing for a lot of people, including me, when I initially started learning these. So be careful about this difference between what is a forward pass in diffusion and which is different from the forward pass in the actual neural networks training. So what does forward pass in diffusion do? It says, let's take an input X. Now I add noise to this input X. Let's say I add noise epsilon, which is sample, let's say, Gaussian distribution. Now the output will be a slightly like, let me call it x1. This will be like slightly noised version. So if you take any image, you add Gaussian noise on it, what would it look? It look like random white noise on top of the image, right? So I'm just drawing it for visualization on the right side, top right. Let's say you have original image like a man, and then you add some noise. Then what will we see? We typically see like dots because of the noise which you just added. So this is how the noise will look like. Now forward process keeps on adding it, like you keep on doing this until the output, let's say xt, this is nothing but a complete noise, like it is coming from a Gaussian distribution. So we keep on adding noise until our input, which was x, completely gets transformed, like it is coming from a completely random process, like Gaussian distribution. So this is the goal of the forward process. Now why do we do this? Because at every point when we are adding the noise, we know how much noise has been added, and what is the output by adding this is the noise. So if you can subtract that particular noise, in reverse process we do the backward. So if we go from here, we start off from a random noise xt, and we keep on subtracting the amount of noise that takes place in every step. And how do we know how it will change? That we learn in the forward process. So by removing that much amount of noise at every step, the goal is you will end up with this exact, which will be very similar to x, by subtracting the noise from the xt, from the you sample a noise, you keep on subtracting noise until you come to the original distribution exact. So this is the overall back forward process and reverse process of diffusion. Of course there's a lot of the objective function involves the actual modeling, sorry, it involves a lot of math and how you get these loss functions and everything that I hope you all watched the lectures. I just want to give you a high level process. So based on this idea, let's look into the questions, and then we'll also implement a diffusion model. So I'll show you how exactly neural networks come into play in this forward and reverse process. So to give you a very simplistic answer, neural network will learn what is this noise that gets added, such that it will transform the input to the output x1. That's what it is trying to learn. What is that noise level that is present given a particular input and given a particular type of an output? That is what we're trying to learn. Okay, any doubts until now? Any clarification, something that is not clear, something you want me to repeat? Okay, so if this is clear, then let's go to the questions. Okay, first question, very simple question. Which of the following represent a valid transition matrices for a Markov process? I hope you are aware about the Markov process, which is we discussed in the diffusion models in the starting first, I guess the first lecture of diffusion models. So based on that, try to answer which of these are the valid transition matrix for a Markov process. So I'll pause for a few seconds, try to attempt this question. It's okay if it's wrong, but please try to attempt so that you'll know where your understanding is going wrong. Yeah, A is correct. There are multiple correct answers. A is correct. Apart from that, use the same logic which you used for A. Try to identify the other transition matrix which can be valid. Yes, the correct answers are A and D. So, what firstly, let's talk about what is a Markov process. So, Markov process, let's say if I have you, sorry, we all must have seen these transition diagrams like in our undergrad. We are usually very familiar. Let's say we have three states, let's say A, B and C. This could be anything. The typical example for these states you can think of like a vending machine state. Okay. A vending machine, if someone wants, it'll usually be in an idle state like A. Then someone wants something, they press certain button, then you go to state B into identifying what they sent, and in step C the transaction will be done. You could be any, I'm just giving vending machine, you can think of any states, any process like this. And then there is a probability in going from one state to another. So let's say the probability of going from state A to state B. This could also be like your typical game when you're playing game. Imagine it to be a simple three states game. Okay, there's nothing much, and let's say there are some external factors with which you can either go to state, from state A you can go to state B, and from state A you can go to state C. Now what is the probability of you going from state A to state B? That is an external environmental condition. And let's say we are given those information, like let's say we have like 0.9 probability from going from state A to state B, and similarly from state A to state C you have like 0.05, and then there's another probability that you can just stay in the state A itself like 0.05. Now similarly you have for from state B also to go to state C, and then similarly for state C also we have certain way. Okay. Now based on this probabilities, we create a matrix called transition matrix, which is typically it's represented like PT. Okay. And what does this transition matrix even represent? So it'll be the same A, B, C. The columns will also be A, B, C. Now rows can be thought of from this. Let me write it properly. From this particular state, the columns will be to which state. Okay. So if you're at A, state A, and if you want to go to state A itself, like stay in state A, what is the probability? 0.05. Similarly, if you are in state A and you want to go to state B, the probability is 0.9. And similarly, if you're in state A and if you want to go to state C, the probability is again 0.05. So in this way, you complete the entire matrix. So this is a transition matrix. The name suggests like what is this transition matrix basically tells you the probability of transitioning from one state to another state. And since it's a probability, the only bigger, obviously the three conditions, but one of the main condition is the sum of all the rows should be equal to 1. The sum of all the row elements in the row should be equal to 1 because it's a probability. And that is why it should sum up to 1. And the other conditions are each element should be a non-negative number. It could be either a 0 or positive. It should not be negative. And also the transition matrix must be a square matrix. It should always be an n cross n matrix. If it's rectangle, it doesn't make sense. It's not like some states are suddenly appearing out of nowhere. It might be possible. There are some other cases like I think partial MDP and something, but for actual Markov processes, it's always a square matrix. So all you had to do in this particular question was identify which are the rows which sum up to 1. In first A, it sums up easily, and again D also it sums up. Since all of them are square matrix and non-negative elements, so you don't have to worry about the other two conditions. Okay, I hope this was clear. If there are any doubts, please let me know. I'll move ahead in the interest of time. Okay. Now, this is again if a very simple question based on the forward process of the diffusion kernels. So, given these four different possibility of distributions that you can model the diffusion forward process, which particular diffusion forward process will actually converge to a Gaussian distribution? When you're going from xt minus 1 to xt, that finally the final Gaussian distribution which you want to achieve. You start off with an original input image, you want to add noise until it reaches to a Gaussian distribution. The question is which out of all these distributions will actually lead you to a Gaussian distribution in the entire forward process. The convergence will reach to Gaussian distribution. So again, multi-correct answer. Read all the options carefully and let me know. So here, maybe let me give you a hint. Linear decrease, cosine decrease. This is beta is a parameter. So beta can either keep on decreasing or increasing based on at every time step based on the policy you follow. So beta, you can think of it just like a hyperparameter for this Gaussian distribution or Poisson or Dirichlet distribution. Okay, let me explain. So the answers are A and B. So typically you can get this by quickly solving something called as a recurrence equation and look at how it converges. So even forget about that. So there is something called as a reparameterization trick for Gaussian distributions. So let's say, what is that trick? Let's first understand. Let's say you have xt is modeled by a Gaussian distribution mu and sigma. This is one way. Another way which we saw last week also, the same reparameterization trick we used in VAEs also. What did we say? We can also write xt to be mu plus sigma multiplied by some epsilon, where this epsilon is coming from a standard Gaussian distribution. This exact reparameterization was used in order to make VAs actually optimizable using gradient descent. Now, similarly, you can also model your Q function of xt given xt minus 1 as a Gaussian distribution of mu and sigma. Now, here, what is this Q of xt given xt minus 1? Think of this like the transition thing, right? Like we just saw, what is the forward process in um, what is the forward process in diffusion? We start off from x0, which is the original input image. We add a noise, epsilon. We go to x1. Then we add another noise. We go to x2. You keep on doing it until we reach xt. And before xt will be xt minus 1. So if I want to model this process of transitioning from one state to another state, just like I just talked about transitioning matrix, right? So if you want to identify what is this transition matrix, you need to model it somehow. So we say, okay, I'm modeling it as follows: Q of xt given xt minus 1 will be some distribution. That is how I'm modeling. For now, we'll ignore what the distribution is. We want to follow some distribution. Now, what do we ideally want? We want the original x0 to reach to xt, and this xt is a Gaussian distribution. Now, the question is, what should be this modeling of this q such that we reach a Gaussian distribution? That is a actual question which we have. Now, obviously, if you use a standard, if you use a normal distribution, you will, but this normal distribution has certain conditions such that it will reach the standard normal distribution. What is that condition? That sigma should always be bounded and mu during convergence will go to 0. Bounded in the sense it usually bounded to 1, basically. It goes bounded to 1, and mu in convergence should go to 0. Now let's go back to the options and analyze. So this is the condition. We want mu in convergence to go to 0 and sigma to be bounded, more or less the norm to be 1. Now typically in diffusion model process, we have the first so this parameter you can ignore for now. It is just saying that this is the parameter xt used in Gaussian. That is not of relevance right now. The other two parameters are important. The first one is mu, the second one is sigma. What is mu beta over here? Beta, if you in typically in a Gaussian diffusion process, beta t is between 0 to 1. And if you keep on reducing it, so we are linearly decreasing, right? So beta will eventually go to 0. It can't go, it is, since it's decreasing, and the least it can go is to 0. In convergence, this particular beta value will go to 0, and will go to 0. Now 1 minus beta, if beta is going to 0, 1 minus beta will also go to 1. So this is exactly what you'll achieve. You'll come to eta of 0 comma 1, which is the convergence to standard Gaussian distribution. And so first one is the correct answer. So this is one way to quickly solve the problem. Another way is mathematically you actually solve the recurrence equations, but this is a more intuitive way of solving the problem. Same idea we can think of with cosine problem also. Cosine problem, you transfer between -1 to 1 and you follow the cosine schedule. So this will, since square root of 1 minus beta, and this is a cosine, not linear. So this will again go to 0, and this will also bound to be 1. And second one option is also correct. The third ones, Poisson and Dirichlet, can actually never become Gaussian distribution because both of them fundamentally are kind of discrete in nature, and they can actually never become Gaussian distribution. So the other two options are wrong. So I hope you were able to understand how to solve such problems. Any doubts, please let me know. So it is dependent on cumulative alpha. So that's what I said. So you can solve the recurrence equation. That is where the cumulative alpha will come into picture. So that is a more actual rigorous mathematical way to solve. But if you want to understand what are we even trying to achieve when we say convergence, we ideally want to this mean to go to 0 and this variance standard deviation to go to 1. So this is a more easier way to approach this problem. You can always try to solve depending on the cumulative alpha, because we model in diffusions, we typically model, I think, alpha t to be 1 minus beta t, and then you keep on solving the recurrence equation from 0 to capital T, where alpha t will go to alpha t bar, the cumulative alpha. So you keep on solving that mathematically. That is also one way to solve it. I hope it answered your question. Okay, let's move to the question 3. So there are 4 statements given, and the question is which of the four, again, four statements related to different diffusion models. One is the standard discrete diffusion models. The other is classifier guided diffusion. Another is classifier free. So based on these 4 statements, try to identify which of the following are true. Read every statement carefully and try to take answer this question. Okay, couple of answers. Yeah, I think D is not the right answer. C is the correct answer, as pointed out. So let's go and look at each particular statement first. So, firstly, what is a scoring function? Before even talking about other options, we need to know what's a scoring function and what is a true scoring function that we're trying to achieve. So, scoring function is nothing but the gradient of the probability of x. Okay, it's like probability of x is trying to is the distribution of the input. The gradient of probability of x is nothing but the score function. Okay, I hope that definition is clear. Now, what is the first point saying? DDPMs, which is nothing but the uh, discrete denoising. I forgot the full form, but yeah, it's basically the standard discrete diffusion models. Those explicitly learn the true scoring function concerning the data distribution. It's not true. What discrete diffusion models actually learn? They are learning the probability of that x given a particular time step. So technically, they are learning this score. They are not learning this score. So this is not a true score function. You're learning a time dependent score value, you're not learning the actual score value. So that is why discrete is not true. Why? Because at every time we are trying to identify what is the output, right? By adding the particular noise. So that is what we're trying to understand over here. We're not learning the actual true distribution, the actual true score function. Sorry. Then the second option says in classifier guided diffusion sample, one learns the true score function in a supervised manner. Okay, so it's slightly tricky over here. So classifier guided sampling always learns in a supervised manner. So again, I'll give you a high level overview of this particular classifier. So there are two parts. One is your standard uh, learning of p of xt. The other is learning. Sorry, let me write it properly. Yeah, it's learning p of xt plus you also learn the classifier. Okay, and where is this classifier coming? So typically there are two parts in classifier guided diffusion. First part, you learn the diffusion models as it is using the same discrete diffusion principles which we have, right? I'm just writing standard way. That is, there is no classifier control or anything. Just learn it in the most standard way without any external supervision. Second, you learn a classifier y, this classifier probability of y given x. Now, how do we learn this classifier? So at every step in the forward diffusion process, you have this xt, which is slightly noisy version of the original image. You have the associated label with it. And then you learn this classifier, give this to a classifier as an input, and you predict some y hat, and you do normal supervised classification view, right? And then we learn how far away is y hat from the actual y. Now the problem is this xt is not the actual x. Okay, actual x is has the label ground truth y, so we expect this classifier to work perfectly. But this xt, if you think about it, as and more we move in the forward process, xt will become more and more noisy. So the, if the classifier is not predicting it correctly, it is not because the classifier is wrong, it's because the input itself is changing. So it might get slightly tricky in how you can optimize this better. So that is why this is not a very simplistic way to solve, because you're kind of having this xt which itself is not the true x, and we are building a classifier on top of it. It might not be our actual supervision that we want to enforce. But that being said, again, all of these steps in this formulation, it is all time dependent. So we are not learning again the true scoring function. We're all learning a time dependent values. So again, option B is also wrong because it says you're learning the true scoring function. While supervised manner is true, the true scoring function part is wrong. So A is wrong, B is wrong. Now C says one can usually sample data from images faster than diffusion models. Absolutely correct. That is exactly what GANs VAs do. They kind of do it in one step, right? If you think about it, VAs, you do forward during the inference time, you send the input, you know the mu and sigma values which you learned during the training, and then you get the output from them. In similarly for GANs also, you train the generator network, and you give you take a noise, you give it to the generator, it predicts an output. It's one forward pass, right? Inference. In diffusion, if you remember, how are we generating images? We're generating images like we start off from noise x capital T, then we keep on eliminating the noise minus some noise, then x t minus 1. You keep on doing it until you reach x0. So this has like a lot of steps. Sorry, this is not like a one single step. This has a lot of steps. So even though there are some techniques in the more recent times where they optimize the number of steps, like they kind of reduce it number of steps during inference time to get the actual output, still it was there are GANs and everything which are faster than the diffusion models in sampling data from the diffusion models. So option C is correct. Now, this option D says classifier based diffusion models work better than classifier free ones because in the former explicit supervision, whereas in the later there isn't. Again, what I said, the supervision, while it might be very helpful in general if you think about it, because we always want supervision, right? Um, because you know what is the correct answer, so it will definitely help in solving the problem. But here the supervision itself might not be very helpful because the input xt is not really the actual x, it is a noisy version of x. So whereas in classifier free, so let me write down the classifier free version. So in classifier free, you learn basically there are two stages again in two steps in that also. You learn the diffusion model in the standard way, plus in the second, instead of learning a classifier, you also learn the diffusion model in a conditional way, conditioned on the class y. But it'll still be in the standard way. You're not having an extra external classifier, but you're just conditioning the diffusion model with that extra class term, but using the same old loss function formulation itself. So that is why in classifier free it is slightly better, and actually most one of the most popular methods also, classifier free, where you don't use any external classifier at all because external classifier might get tricky because of these xt changing. So option D is also wrong. So final option is only option C. These are the same explanations which I just talked about. You can look at it in your own time. Okay. Now let's go to question 4. Okay. Again, you have 4 statements. Now you have to identify based on the same diffusion model itself. Identify which of out of these 4 are false statements. So I'll quickly pause for a minute. Please read carefully and try to answer. Okay, the multi correct answers. Option A is false, true, but multiple correct answers are possible. Option D is also false. Correct. N- Is there any other statements? Yeah, I think already pointed out A, C, D are the wrong answers. I mean, are the false statements, so they are the correct answers. Option B is the actual correct answer. So let's see what quickly, because most of them already have explained about the diffusion models. If you understood up till now the diffusion models, how they overall work, it's pretty much straightforward. So first one says it can only generate samples directly from the training data. Not true, because the entire point of diffusion models is to learn from a distribution, not the given data itself. So of course, A is not true. And option B is actually true. There is a actual theory in how diffusion models come about is they come about from something called as stochastic differential equations, SDEs. So when you try to solve the SDEs, you come up with a bunch of flow based algorithms. And one such flow based algorithms, when you use a particular process called like Wiener process, that is where you create a generic diffusion process. So this is more about the history of diffusion. So if it's not relevant in the recorded lectures, it's good to I have this idea where exactly diffusion processes come from. They originate from stochastic differential equations, flow based algorithms and all. But more focus is on what actual formulations of diffusions we looked at. So option B is actually true. Then option D says diffusion models sample based on ancestral sampling. That is not true. We sample in the forward pass based on that noise which we take, and then we subtract it. Then the option D says score networks predicts one learns a score network which predicts the mean of the each intermediate distribution in forward diffusion process. This is actually not true. I will show you in the algorithm next that we actually predict the noise in the in the training time in the forward diffusion process. So option D is also false. Okay. Now let's go numerical. This is a very interesting numerical, very simple to solve. The question 5 says in a standard diffusion forward process, if the data point is initially set to 3, the noise variance beta is fixed at zero point 0.4 for each step. So beta t is a fixed value, it's a zero point 0.4 for each step. How many time steps would it approximately take for the variance of the noise samples to reach 0.99? Okay, so try to attempt this particular question. Oh, there's a question in the chat. uh, Oh yeah, so ancestral sampling. So we sample in the backward pass. Okay, let me go back to the previous question. So here it's saying that ancestral sampling is done in the forward pass. That's not true. Ancestral sampling is kind of done in the backward pass. That's when you sample the diffusion models. You don't sample in the forward pass. So that is the problem. We do it in the reverse process of diffusion. So that is the wrong part over here. I hope that is clear. The problematic statement over here is the forward pass. That's not done in the forward, it's done in the reverse pass. Okay, any guesses for this particular question? Answer is close. It's 9. Let me explain. It's very simple. So we model variance as 1 minus alpha t. And if you know what alpha t is, we just saw alpha t is nothing but 1 minus beta. I'm ignoring the t subscript over here because it's all fixed. It's a fixed beta, so I'm ignoring the t over here. So what is the variance? Variance is 1 minus of 1 minus b over a time steps to the power t. Now, given that beta is equals to 0.4, and we need to find the t such that the variance is approximately 0.99. So you just have to solve this equation. 1 minus of 0.4 whole to the power t is equals to 0.99. This is nothing but 0.6 to the power t equals to 0.01. And if you solve this, you'll get t is equals to 9. So in 9 steps, you are able to go to a variance which is equals to 0.99. Okay. All you have to remember is this formulation of variance. And I think once you understand this formulation of variance, I think you can just equate it to what value you want and solve the equation. Okay. Then let's move ahead. So this will be the last MCQ question. Then we'll go to the coding part. Very simple. Yes or no question. When training diffusion models, does the learning remain invariant of the weights of the reverse process time steps? Try to take a guess for this question. Yeah. The answer is no. So what is happening? The reverse process and diffusion models is usually parameterized by neural networks that predict the noise of the data given the noisy input. That is what we're trying to do. Because once you predict the noise in the reverse process, then you subtract that noise from the given input, and that's when you get a slightly cleaner image. And you keep on repeating it until some t time steps to get the final image generated. Now the reverse process is conditioned on time step t, because at each time steps t, you need to understand, given the time step, what will be the noise. So the weights of the neural network are not completely invariant to the reverse process because they're dependent on the time step. So the entire reverse process is time step bound and the weights are dependent on the time step. So it is not completely invariant to the particular reverse process of diffusion model. So that is why the answer is false. There is no invariance. In fact, there is a dependency of the learning weights in the reverse process time step. Why? Because the goal is at each time step you predict a noise from the neural network, and this noise is particular for that time step, and that you subtract it to get a cleaner image. Uh, if you want, maybe let me just write it down also. So you have a noise xt. The neural network predicts. Uh, I'm just writing like this. Predicts epsilon. You How do you get xt minus 1? This xt minus 1 is basically let me write it this way. Xt minus epsilon gives xt minus 1. And again the next time, so this is on time step t. Neural network, so neural network conditioned on time step capital T. And you keep on repeating this process. At every time step you predict the noise and then you subtract it to get the final clear image, and this entire process is the reverse process of diffusion. Okay. Any doubts in any of the questions we discussed today? If not, we'll move ahead to the code walkthrough.
So where the differential equation come into picture here, because we have that equation, right, to predict one state from another in forward process. So
Okay.
then where the differential equation is, it to how much noise I need to add at every state, or when
Yeah.
that comes into picture?
So let me go to the equations itself in the code we have. So this is typically how we model everything. So we have the original forward processes when you go from x0 to xt, and reverse processes when you go from xt to x0. And when you're formulating, I think you're talking about the formulation of Gaussian distribution. These, right? X of t given x of t minus 1 is equal to Gaussian distribution of these. And similarly, the reverse process, we model it using p theta, which is a parameterized version, which is the distribution we want to learn, which will take us from a noise to a cleaner image, t minus 1. Again, this, how we parameterize using a normal distribution. Uh, okay, is this clear?
Yes.
Yeah.
But then differential, we talked about differential equation somewhere, right?
Oh, you talk about stochastic differential
Yes,
equations.
yes.
Okay, so that is not present over here, and the derivation is also not very simple. So I would maybe suggest you some resources. There is a very good course from MIT which talks about diffusion models and stochastic differential equations. So it starts off from a pure mathematical SDEs, how to solve. It starts off from ODEs, actually, ordinary differential equations, then goes to stochastic, and then connects to diffusion models. It's an entire course in itself. I don't have those equations over here. Yeah.
Okay.
Yeah, I can maybe refer you that. I'm not, I see, if it's not there in the recorded lectures, then you don't have to worry about it. I just kept it so that you everyone can get some idea, like where is it coming from.
Okay.
Yeah.
Got it.
Yeah. Okay. So yeah, let's go to the code itself. So here we are trying to uh, so you can look into the actual notebook itself. We have the links and everything from where this particular notebook has been created. So we try to look into DDPMs, which is denoising diffusion probabilistic models. Uh, So we try to implement the paper in 2020, this denoising diffusion paper. And obviously, it's not complete implementation. Some slight simplistic assumptions are made in this particular notebook. So like I said, so this point, right, there are several perspectives on diffusion models. This is the point where I was talking about SDEs. So one perspective of diffusion models comes from the stochastic differential equations, how that connects to what we saw in the actual formulations of diffusions, this classifier free, classifier guided, and all those things. Yeah. But here we stick with the time, a discrete time latent variable model perspective, which is proposed in this paper. So one important part which you all need to know is, originally this idea of diffusion was proposed in 2015, but they didn't really call it diffusion models. Then it took some, like, I think 2019, 2020, there were two papers, and then they independently improved the 2015 paper and they came up with these names. So that's why there's a good history for diffusion models with different perspectives. Anyone who's interested can definitely look into these papers and can get more understanding about these models. Okay, so as usual, we import necessary libraries. I think at this point everyone is aware about all these libraries. So some new libraries we see, I'll explain. So Einstein operations is this EINOPS, it's called Einstein operations. So these basically try to do your same reshaping, matrix multiplication, vector multiplication in even simpler fashion. So that is where this comes in. We'll see how you can implement an attention, a transformer attention, so transformer architecture, actually multi attention, using these Einstein operations. So even I'm still learning about this. So you can ask me questions. I'll also try to answer as much as I can. It's very simple. The documentation is very simple, but it's very easier to what we saw previously, right? When we were implementing transformers, that is Also correct. That is also one way to do it. Probably you write 3 lines over there, you write 1 line over here. That is the only difference of using this library, nothing else. Yeah, I think others torch based functions libraries are pretty straightforward. So I think I already discussed this, but let me be again very clear. So there are two processes in diffusion: forward process, reverse process. In forward process, you take a clean image, you keep on adding noise until it becomes like this, like a proper noise, which we assume, let's say, Gaussian noise. And then in the reverse process, you start off from this Gaussian noise, you keep on subtracting noise from this noisy image, and until you reach a clean image. So we know so now we have to, this is a transition, right? You're transitioning from one state to another state, so you can obviously use transition matrices, and each transition matrices is nothing but a probability distribution. That's what we saw in the first question. We know how the transition matrix will look like when you're going from Q to Gaussian noise. We can model it: Q of xt given xt minus 1. That is, given a clean image, how can you get a noisy image? That is this Q. If you want to go to no, Gaussian distribution, we saw that we can model it like this. Why? Because in convergence, this particular equation will lead us to a standard normal distribution. This was a question too. So yeah, and this particular information is available to us during the entire forward process. So Q is not like a something which we don't know. Q is something which we know, which we can model, because all of these parameters are something which we can which for the values which we have. The things which we don't have is the reverse process. That is the p. Ideally, we call it p of xt minus 1 given xt, but of course we don't know. We approximated with theta, p theta. So this is the reverse distribution, backward distribution or reverse distribution, which we kind of approximate or parameterize. Instead of approximate, let's call it parameterize. The process is parameterized using this formulation: p theta of xt minus 1 given xt. So this is like, given a noisy image, how can I get a clean image? No, it's not how can I get a, given a noisy image, what is the probability of getting a clean image? And that you again model it with a Gaussian distribution. And here we don't know the parameters. That is why we have the mu and sigma to be like, you don't know the actual value, so you parameterize mu and sigma. Like, mu theta is the parameterized version of actual mean, sigma theta is the parameterized version of actual uh, variance, standard deviation. And you can see both mu and sigma are dependent on time. Okay, so very important thing, these all of them are dependent on time, because based on that particular time step, there is a certain level of noise that is present. Okay, now how do we define the objective function? So we define the objective function. Firstly, we rewrite beta to be nothing but alpha to be nothing but 1 minus beta. Then we can rewrite this entire thing as root of alpha t bar, which is nothing but the cumulative, it's defined at the bottom, cumulative alphas, and 1 minus alpha bar ti. So now we replaced the beta terms with the alpha terms for convenience. And then we apply the elbow loss, which is nothing but the sum of losses at each time step: L0, L1, L2, L2, so on up to L capital T. Now, what is that loss? Uh, s- yeah, yeah. So this is what the final objective function which we have. So we basically try to predict epsilon theta is trying to predict the noise at time step t. Epsilon is the actual noise that is being added. So if you this is like a mean squared loss, right, between them. So we want the prediction of noise to be close to the actual noise that is being added. Then we use the simple mean squared error loss between them. And how, where is this epsilon t coming from? Epsilon t is coming from the mu theta, which is the mean of the neural network which we want to predict. Because variance, we're keeping it simple, we're keeping it standard fixed value. We're trying to predict the mean, and the mean sorry, we reform this mu theta into the epsilon theta, which is trying to predict the noise. So all in all, what we try to do is the following. In the training time, we take an input x, which is coming from the data which you have. We take a time step t. It could be anything. It doesn't have to be sequential 0 1 2. We don't have to go that. We can take any time step t. You take an epsilon. This is sample from normal distribution. Then you try to take a gradient along this loss function. Gradient along this loss function, epsilon, which is the actual value which you'll add, minus epsilon theta, where the input is x0 added alpha bar t plus 1 minus of alpha t multiplied into epsilon at this particular time step. So this is like, if I add a noise at time step t to this particular input x0, how much is that noise that I'm adding epsilon t, right? That is what I'm sending this entire input. And what is that noise that has been added to this particular input? That is what the output from epsilon theta will come, and which should be close to the actual epsilon which we're adding. Okay, I've said a lot of things. Is this idea clear of what we're trying to achieve? This is again very clearly explained in the recorded lectures, but please let me know if anything is not clear or anything you want me to repeat. So maybe let me draw it once to make it more clear. Okay. So x0, let's go to x1. Let's take 2 steps. Okay, 3 steps total. I'm adding, ideally it's not epsilon 1 epsilon 2, but for our simplicity I'm writing epsilon 1 epsilon 2. Okay, this is the forward process. Now how I'm getting x1? X1 is nothing but some mu value x0 plus epsilon times sigma. This is the reparameterization trick which we talked about. Okay, now sigma, again we keep it fixed so we don't have to worry about it. Now this is how x1 comes. Now similarly x2 will come with some mu of x1 plus epsilon, and you can substitute the x1 from here. So you can think of this to be like mu double prime. I'm not writing an actual definition, I'm showing you how it can form. That is the idea over here. So you'll get some terms, let's call it like some uh, constants type of terms, x0 plus epsilons and some other constants. Okay, so this is x2. So you see how at every time step you can connect back to the original input x0, because because of this reparameterization trick of Gaussian distributions. And now what we are doing in the training time, we are saying, I'm writing it on the left side. We're saying, okay, take your input x, you sample it from your distribution, which is the data which you have. You pick any time step t. Okay, from the entire uniformly, you can pick from this 0 to t any time step, and you pick an epsilon from the standard deviation. Now, if I want to know what is x of t, what is x of t? X of t will be nothing but some constants mu times of x0 plus epsilon. Okay, multiplied with the time t. Not multiplied. This will be the xt value. Let me make it better. This will be xt value. So you want to understand what is that noise that has been added to xt. We don't know where xt is coming from this distribution. So we added some noise and we're getting xt, but we want the neural network to predict what is this. So neural network, I'm writing it on the top, which is like epsilon theta. This is the neural network. This will take the input xt, which is that normal distribution, and tries to predict epsilon hat. So xt doesn't, when you're showing xt, you're not actually showing the epsilon. You're adding that epsilon, getting the xt, and you're sending that xt as an input to neural network. And now neural network needs to predict a noise that has been added to xt. Let's say it also knows what is x0. It tries to predict the noise that has been added. Now, this noise should, we know the ground truth, right? How much noise has actually been added to xt, because you know how xt is formed. So we know the ground truth. So this xt should be as close as possible to the actual noise that has been added. And how do we measure this closeness? The most simplest way is the mean squared error. So this is how the training pipeline happens. So this is the training pipeline, the one written in black. But the idea of why we are doing this way of training is because of this way we formulated the forward process, and how we are trying to predict the noise. So I hope this is clear. Any doubts in this? Okay. Then let's go to the code itself. So we just have to implement this step. So importance of which sampling? We have two samplings. We have time sampling and noise sampling. Which sampling are we talking? Oh, noise could be. So we need noise. Why? Because we want to corrupt the image, right? We want at the end of the day to, if you predict the noise in the reverse process, so during the training time, you need you need to corrupt the image. So that, for that, we're sampling the noise. And why do we have to corrupt the image? So that we make the neural network predict what is that noise that has been added in to make this clear image as a corrupted image. Now, why we want that neural network to learn this noise? Because in the reverse process, this is what will be predicted. So given an noisy image, neural network will predict, okay, at this time step, this is the noisy image, so this will be the noise that has been added. Now that noise will be subtracted from the noisy image. So we know we need to predict that noise. So that is why we're first corrupting. And how do we corrupt? We corrupt using this epsilon, which has been sampled. So I hope that pipeline is clear of why we are doing this. No, no, epsilon doesn't. So every t we sample a random epsilon, but epsilon itself doesn't depend on any t. But every t will be new epsilon, right? We can't use the same epsilon, because if think about it, it's like you're giving the same type of input to neural networks, so it will easily learn because there is no random pattern over there, right? You're telling all the inputs are the same input, so it will learn what is the corresponding output. So it can easily predict epsilon. Here you want to add more diversity to different levels of noises, different types. What do you mean by different types of noises? Each time you get an epsilon, it'll be a different value. So it's just like how you're getting apple class, cat class, dog class in your traditional neural network classification. It's just like that. So if you keep epsilon fixed, it's like, imagine it to be a one class problem, which is not really helpful. Okay. Was there any other question? I think someone unmuted also.
Yeah, so I heard about this thing, linear schedule, or decreasing by linear way, or decreasing through cosine schedule. So
Yes, yes. So what happens over there is, I think I have an image. Okay, I don't think I have an image. So I'll show you in this way only. So you see, when you're going from clear image to noise image, there are different. See, you can add a lot of noise in the starting steps to make it reach to a noisy, faster way, right? Or you can add slowly, little bit of noise, and it'll take a lot more time steps to reach to the noisy image. So the frequency or the intensity at which this happens, that is the scheduler. So if beta follows a linear scheduler, it means it will quickly reach to the noisy image in fewest time step. But if beta is cosine, that's what the one of the papers says, using a cosine scheduler, beta takes the noise, for it to become a noisy image, it takes more time steps. So, and it is better if you have cosine, is what they found out empirically, because it is better if you add the noise slowly rather than adding it in a more linear way and quickly reaching to the noisy version. So that is where you heard about schedulers.
got it. Thank you.
Yeah. Okay. Yeah. So now the question is, what is this neural network epsilon theta that we will use? What do we want to do? We want to predict noise. We have an input So we have to ideally reconstruct that input from x. Given x, you have to want to reconstruct the input, and the output will be basically the reconstructed. Sorry, what I mean by that is we want to reconstruct the output to have the same dimensions as the input dimensions. That is what we want to do, because then once we do that, we identify the noise level at each pixel. That is what we're finally predicting. Now, what are the methods or algorithms which we saw previously that will reconstruct the output to have the same size as the input? One of the popular ones is unit architecture. And in fact, the DDPM authors actually go for a unit model itself. So this was the unit architecture, which takes the input, and the idea of a unit architecture is the encoder will keep on reducing the size until it reaches a latent space, or a latent vector. And from here, the decoder block starts, and the decoder keeps on increasing the size until it reaches the same dimensions or the resolution of the input image. And once you do that, you now each pixel level, you identify what is the noise, and you calculate this epsilon minus epsilon theta for each pixel. So implementation wise, it's very simple, in the sense, like, not the training, but the idea. When you look at the training, it's literally just 4 steps, and you already we already implemented a neural network unit architecture previously. It's just that to come at this formulation, to come at this loss gradient and everything, that is where the slightly complicated diffusion part comes in, to understand where how we are actually doing this. But once you understand why we are doing it, implementation wise, it's not very complicated. Okay, so let's look at the unit implementation, which we previously saw, but let me again reiterate for completeness sake. So we first have some bunch of helper functions like residual connection, because if you remember, unit also has the skip connections, right? So we need the skip connections over here. We also have upsample, which function, which will basically do nothing but it will apply the convolution transpose 2D operation. Downsample is applying the standard convolution 2D operation. So why we use these functions, it's easier to call them. Otherwise, we can also write this, but we have to keep on writing this multiple times. We just use this to keep it simple. Okay. Now, one other thing what DDPM also did was to add positional embeddings, just like how transformers have positional embeddings. Why? Because of the positional embeddings, they want to understand the different noise levels, right? Because there is a time dependent on noise. So just like how positional embeddings played a role on understanding the time dependence, they also add over here the same sinusoidal positional embeddings in this particular uh, uh, unit architecture. Now let's define the core unit block. So the authors use something called as wide ResNet block. You can look at the paper, and they also took support from convnext block. Convnext is like a much advanced version of the typical convolution neural networks. I think it is still one of the most popular, just like how ResNet, InceptionNet was there, right? Convnext is also like that, I think, but it is still very popular among convolution networks itself. So, if I'm not wrong, Connext, the idea was transformers were good at forming these correlations between different patches of the image. If you remember VITs, they tried to form the patches of the image. But the problem with transformers was they were not learning the representations in the way convolutions did. That is that spatial invariance, translation invariance idea, right? That is lost in VITs as soon as we make the patches. Convnest basically takes the best of both worlds. It uses the principles of this attention mechanisms, but still uses convolution operations. So that is where it works the best. And I think I'm not sure about the exact architecture. You can look into this paper for more details. So yeah, unit also uses the wide ResNet block, and also it takes support from convnest blocks. So for ResNet block, we have these two blocks, block 1 and block 2. And what are these blocks? These are again nothing but defined on the top. So each block consists of a convolution operation, a group normalization operation, and an activation function. CLU is another activation function, just like how ReLU is. This is another activation function. So one important thing, again, everyone knows, but each neural network what we're defining needs to inherit this nn dot module. Otherwise, your PyTorch won't understand it's a neural network class. So you first define the smaller unit block, and then you call this block into the ResNet block. And the forward function basically does that. It basically takes the input, sends it to block one, and then it appends the time positional embeddings, and then it sends the output to the block 2, and then it does a residual connection. Similarly, connext block has the following layers. It has an MLP layer, which is one sequential layer, and if time embedding exists, that also. Sorry, it's one linear layer, and one GELU is another activation layer. Then we have a convolution layer, and overall network looks like this: one group normalization layer, one convolution layer, one GLU activation, one group normalization, another convolution. So here the same, you take input X, send it to the first dscon block, which is convolution, take the output, and again send it to the if time embedding exists, you pass it to that, and then you add it to the h value, and you send it to the second block, and then finally you again take another addition, residual connection, and you return it. So there's not much happening over here. It might be hard to understand because we're not familiar with the block architecture, but that is not the point of uh, the diffusion over here. The principle of diffusion works with any neural networks in practice. This is the best way to do it because it's a more optimized neural network. You can ideally do it even with MLPs. It's just that it might not predict the noise well. So people have identified this is the architecture which will predict the noise much better than MLPs. So all these architecture details, you can go in through these papers to understand what the architecture is, what are the layers. So once you understand the layers, you just have to write them like just how we created other neural networks, right? Similar way you create this neural network. So one another thing which DDPM authors have done is also they added attention module in between convolution blocks. Why? Because like I said, attention has been very great in identifying the correlations between different tokens or the patches in the input, and so they also wanted to increase the representation capacity of this unit, and that's why they added the attention block. Same attention block which we defined in the transformers architecture. So we have the same vectors, QKV vectors, and we calculate the same softmax scores basically, which is nothing but Q into K transpose divided by root of D. Then we take a softmax of that value and then multiply it with the value vector, and that is the final attention scores which we get. So only differences here, we use this Einstein summation operations and the different ways to rearrange and everything. It's doing it in lesser lines, but if you use the previous way in which we did attention calculation, right, in the traditional way of creating, once we get the QKV, we multiply Q and K with torch dot matrix multiplication. Then you do torch dot nn dot softmax of that value, and then you multiply that value with the value vector v. So you can do that way also, or you can use the simpler way too. So Einstein summation operations, it's slightly trickier in the sense you need, what it's trying to do is it it's very simple in it basically, you provide the two inputs and you say what is the output you want. Like for example, these are the two inputs, bhdI, bhdj. This is the q vector, this is the k vector. This is the dimensions of q vector, this is the dimension of k vector. And what do you want the output? You want the output to be bhij. When does this happen? When di and dj do a matrix multiplication. So Einstein operation says you give in terms of the shapes, and you input shapes and the output shape you prefer, and you mention what are the actual vectors you're using, and you'll calculate it automatically. So you don't have to do torch dot matrix multiplication. That command you're skipping. You're in fact giving in a more simpler way that okay, this is my input shape, this is my inputs one shape, input two shape, and this is what I want. And it will figure out what is the calculation that it has to do. So that is what even rearranged, if you look at BH, So we have these dimensions b, h, c, x, y, and hc is one dimension which we clubbed, and we want to transform it to b, h, c, x, y. So this will automatically map, transform, rearrange it in a very simpler way. So Einstein operations is kind of helping you do the same operations as you did in PyTorch, but with the help of what people want to actually transform the input shapes to the output shapes. So I hope you understand where we're using this. You can use this, or you can also use the traditional way in which we did. Both of them are fine. Okay. Then we also have something called the linear attention, which is similar to the same attention block. We use slightly different formulation for linear, where we do softmax for both qk, and then we multiply it with scale value. So slightly different way of doing the attention, but the idea still remains the same of what the attention is trying to do. It's a much in attention we do cosine similarity. Here, not cosine similarity, sorry. In attention we do multiplication between q and q, then take the softmax. Here we do the softmax individually, and then we do the multiplication with the scale value. Okay. Then there is the group normalization. And group normalization, we usually, so there is, like mentioned over here, right, there has been a lot of debate as to when do we apply normalization. Do we apply it before the attention or after the attention? So you can look into it to get the idea of what is the debate and all. I think you can also try both. See, there's no harm in trying both ways, before the attention or after the attention. Whatever works for your use case, you can do that. Then this is the final unit block which we create with the help of all the other blocks which we just created, like connext block, resnet block, and the attention block also. Where is the attention block? Yeah, these are all the different blocks which we just created. Now this is finally how the forward pass looks like. You take X, send it to an initial convolution, then you add the time embedding, then you downsample it with the different blocks which you just created, connext and connext, resnet, and attention. You keep on repeating this downsample. Then you have a bottleneck layer, which is that in between latent layers I'm talking about. There also you have attention blocks. Then you upsample. In upsample also we have attention blocks. So these three blocks remain the same: connext, resnet, attention. Is just one will do downsampling, one is at the bottleneck, one will do upsampling, and we return the final convolution. So now let's define the actual forward diffusion process. So here beta we use the cosine scheduler. Like someone asked the question, what different schedulers? Linear is also there, cosine is also there. You can try. Or we defined all of them: cosine, linear, quadratic, sigmoid. I think there are even more in recent times. You can look into them. You can. It's like a hyperparameter optimization. You can try whichever is working for you. We define the number of time steps if you're using linear scheduler. Let's say we're using linear scheduler. We define the number of time steps. Capital T is 200. That is what we do. Time steps 200. Betas, we use a linear beta scale. We define alphas to be nothing but 1 minus betas. Then alpha cumulative product, which is the cumulative product. Then previous alpha cumulative products and the square root of alphas values. Same square root of alpha cumulative products. And square root of 1 minus. So all the equations, let me go back to the equations. So all these alpha,
Alpha is the amount of noise that we add to the image, is it?
which, sorry, which value you're
What is
saying?
the alpha here?
Alpha is nothing but 1 minus beta, the variance part, right? So noise is epsilon, but the intensity that keeps on compounding on how much effect that noise should have, that is the beta or the alpha part.
Okay, okay.
Yeah.
Got it. But you also talk about mean squared error, right?
No, mean squared error is not between alpha values or beta values. That is the between the ground truth noise and the predicted noise.
Yeah, got it. Thank you.
Yeah. Okay. So let's say we have the simple image, and let's first look at the forward diffusion process on how we corrupt this clean image with noise. So we keep on adding the noise following the same process of 1 minus alpha t into x0 plus multiplied the variance along with the noise epsilon sample from Gaussian distribution. So first we do some few pre-processing to make that image clear, like we resize, we do center crop, we convert into tensors. Okay, and then here is the no, reverse transform is not needed. Yeah, this is the forward diffusion. This is where you start sampling the q value. Q is nothing but that function, right? Q of x of t given x of t minus 1. So given a clean image, how will the noisy image come? And this is the equation which we just saw. 1 minus of this square root of alpha bar into x0 plus 1 minus of square root of alpha bar into epsilon. That's the exact equation which we are returning. Now we keep on getting the noise image at different time steps. So we write a function where you take the original image, you take the time step, and you want to see what is the noisy image. This reverse transform is basically because you do all the operations in tensors, right? Now you have to convert the tensor back into a PIL image. So that is what this reverse transform does. Originally, you have PIL image, you convert to tensors, do the operations, convert that tensors back to PIL, and you visualize that. So this is how it looks like at time step 40. Given that original image, this is how the noise looks. You can look at various noise levels. So these are the different noise levels: 0, 50, 100, 150, 199. Because at the most you go 200, right? So 199. And you can see how it immediately at 50 only, we are having this level of noise. Why? Because we are using linear scheduler. If imagine we used cosine scheduler, it will probably happen around 100 maybe or 150, like more uh, noise. So that is why the schedulers come from. Okay, now we can use different loss functions. Mean squared error is one loss function, like just like how you can think of it like a regression problem, right? You're trying to predict a real value, and that real value over here is nothing but the noise. In regression, also we either use mean squared error or mean absolute error, like L1, L2 loss or Huber loss, like which is a variant of L1 loss. Anything you want to use, you can use the same way over here also. You just send the first, you get the input image, you noise it, you create a noisy version, you send this noisy image along with the time step to the neural network, and then you predict the noise. And you know what is the ground truth noise because that's what you added. So now you find out noise, the loss between the noise and the predicted noise. This is the entire training loop which we're doing. Sorry, we just calculating the loss till now. Loss till now. You just calculate the gradients and update the network with the help of this loss. So how do we do that? We create the pipeline over here. So first you have a data set. Here we use fashion MNIST data set. It's like MNIST data set, which is like numbers, right? But it is for fashion. So you have a lot of clothing images, black and white clothing images, very small, 28 cross 28 images. So you create the transforms function. These are all standard. I'm going fast because all of these I've explained in detail in all the previous weeks. Everything remains the same. What is a transform function? How do you create the data set? Then how do you create data loaders? What do you have to mention in data loaders? The shuffle, the batch size, all of these remain the same. Yeah. So in this way, you can basically get the data set and train your entire neural network based on this data set. And how do we train it? We already calculated loss. You just have to do loss dot backwards and optimizer dot step, and that will update the neural networks. Now let's look at sampling. So this is how sampling is done. For sampling, you start off with a random noise and you repeat this until t steps. In our case, 200 steps, right? We kept. So for each step, you take a z value from this normal distribution and you send this z. You predict the noise first, and then you subtract it with the xt to get the xt minus 1 value. So you have xt, which is the original noise. Then you predict whatever is the given noise to the neural network. You give it and you ask it to predict it, and it will predict a noise for you. You subtract that noise with a lot of constant terms. You subtract that noise with the original input xt, and you get xt minus 1, and you keep on repeating this until you finally reach x1, which is our until we finally reach x0, which is our final clean image. So the same code which we wrote here, algorithm, it will be written in this function p sample. So here we are doing it for one value where we are subtracting the values. So we calculate the mean and variance to subtract it, and this is the loop value. P sample will do it in a loop completely. Okay, let's first look at the training pipeline. Let me go. So these are very straightforward training pipeline. You create an instance of model, you create an optimizer, you have the two for loops, epoch and batch, and then you calculate the losses. Calculate the loss, then loss dot backwards optimizer dot step, and you can save some intermediate generated images of how your model is doing. So this is how the loss completely optimizes. And then when you're sampling, this is one sample. Again, we ran it only for 5 epochs, so it's not very clear right now. But this is the T-shirt of the MNest fashion, right? There's like a T-shirt that is present in the data set. Again, it's not very good because we just done it for uh, 5 epochs of training. Typically, it takes more amount of training and further hyperparameter tuning. Okay, so definitely take a look at your own time. I know there's a lot of concepts involved over here, but it's definitely helpful because diffusions are one of the popular algorithms in today's world. All of the the image generation which we see, of course, diffusion is not the only way. You can also use the multimodal LLMs to do that, but diffusions nevertheless are still very popular. Okay. Any doubts or anything that you want me to repeat that we discussed in this week? Also, in this particular session.
Yeah, so sampling and training. So first we sample, and is it similar to that? Because we use the concept of shuffling somewhere, right? And there are two algorithm. One is for sampling, other one is for training.
No, no. Sampling is inference. Don't get confused. So sampling algorithm is like inference. Let me go show the two. Training, you do first training, you follow this algorithm. Once you finish training, sampling is like complete inference.
Okay.
Yeah, because we have to generate the clean image, right, from the where is the algorithm? Yeah. Sampling is like proper inference. Like I said, in typical neural network, inference is done in one step, but here it is the entire process, right? So that's why we do this for loop.
Backward process.
Exactly, there's a backward process. Sampling is backward, reverse process.
Okay, okay. Got it. Thanks.
Yeah. Okay. What is the question of convnext? As in, like, do you have a particular question on convnext? So yeah. So let me open the paper once. So as far as I know, it doesn't use a transformer architecture. It takes the inspiration from that, and but it uses completely convolution. But I might be wrong. Let me also just quickly open and check. Yeah, I think it uses completely just convolution layers. That is the what do you say, beauty of this algorithm. Yeah, it doesn't really use any attention blocks. It takes the inspiration from the transformers. It stays only with convolutions. That's why I think it's a much more popular one, because the time to train it and all, it's still in the range of convolutions, but the capacity to learn, it's in the range of attention transformer architectures. But yeah, this paper is linked. Definitely go through it if you're interested for more details, how exactly it is done. Okay, so VIT is not recent. So okay, maybe in terms of timeline, ResNet, of course, is one of the old algorithms. I think probably around 2014, if I'm not wrong, or 2015. Then CNN is older. CNN comes off from AlexNet and all. AlexNet is like older algorithm, 2012. CNN's, I think officially a CNN was proposed in 1990s, I guess, by Jan LeCun and his team. But s- all these algorithms that you see, ResNet, Inception, these are all CNN algorithms. They're just variants of different CNN. So CNN and ResNet are not, you can't say them, like compare them, because CNN is a family of algorithms. ResNet is one type of CNN algorithms. So just like how VIT is one type of transformer, ResNet is one type of CNN. So ResNet came around 2015 time. VITs, if I know it correctly, it came around 2020, and then came Swin Transformer in 2021 or 2022. I think 21, and then this paper came in. Connext came in 2022. So that is roughly the timeline. Probably here and there, but Connext came after the Swin transformer. When the Swin transformer came after normal vision transformers, that's why they're comparing, right? So VIT is not the most recent. Connext is recent compared to VIT. I hope that's clear. Yeah. Okay. Any other questions? Any other doubts? Okay. If not, then
One
yeah.
last. So the diffusion models, when we train the diffusion models, it's not very efficient, right? So recently, what changes are done to optimize it or to make it more efficient?
So one problem was previously people were doing it at a pixel level. People realized doing it at a pixel level learning, right? Predicting the noise might be not very efficient. So people then project it into latent space, like much smaller dimension space. That is where the stable diffusion algorithm. I don't know if you heard about it. That is one of the popular diffusion models still to today's day. Stable diffusion one, two, three. I think three also came out recently. So they, what they do is they project it into a smaller latent space. They use the transformers architecture instead of a unit architecture. They use transformers over there, and they do the same diffusion process, but they do everything in a much smaller latent space. And then once you finish the diffusion, they again upscale it into the original pixel space. That was one popular advancement, I would say, in which diffusions has been optimized. Others are identifying in less number of time step how to do the sampling, the inference process. That is one. And even the loss functions, right? People have changed it. People have made much efficient loss functions. Like there's something called as flow algorithms, flow loss functions, which is much better than the original loss which we just saw. Yeah, there are a lot of, see, I think diffusions is such a popular topic. Every year, every conference, you see so many papers around them. So it's hard to just say like this is the main turning point. Maybe we'll get to know in the few years which was the one which actually helped out in this all this journey. But yeah, apart from that, these are still whatever I told you right now. Those have significantly pushed the research in diffusion models.
Okay, so so CNNs are not completely replaced, right? I mean, this
Uh,
it's a hybrid of both the transformer and the.
so this connext you're talking about.
Yeah.
No, Connext is using still CNNs. They are not using any attentions, as far as I know. They still use CNNs itself. But they way they use CNNs, the layers they're building, that is inspired from the Swin transformers methodology. But they don't typically use a convolution attention block in their layers. So yeah, to answer your question, I don't think convolution neural networks are replaced. I don't think so, because for multiple reasons. Transformers are complex in training. A lot of the problems you don't need such complexity. You can solve it in with simpler problems. So that's where CNNs still shine. But that being said, probably hybrid approaches like convex or maybe something better, because transformers are fundamentally made for sequence models, like token to token. Images are not at all that way. Images are completely spatial dependent. So we need better hybrid approaches that can combine these things, I guess. Yeah, but I don't think convolution, at least in today's time, is completely replaced. There's still research being done in that area too.
Okay, got it. Thank
Yeah.
you.
Yeah. Okay, if there are no further questions, let me stop the